Hello everyone. So in today's class we will be talking about image compression techniques. So it is a very important topic in image processing, right? So in today's class we will talk about what are the image compression, what are the fundamentals of the image compression, and what is the compression model. How can we define the compression in the form of block diagram? So let's go on to our lecture, right? So what actually is image compression? So image compression is the art and the science of reducing the amount of data required to represent an image. Okay, so basically why image compression is required is like to compress the amount of bandwidth that is required for transmitting from one person to another, from humans to machines. So when we are transmitting any images, we need to compress it so that the bandwidth required for it is much lesser. So when we are doing image compression, what actually happens is the amount of data required to represent the image is reduced. Okay, so for example, if we see an image here, so this is the original image, so after compression we should be able to find the image to be the exact same, but the amount of data that is used for representing this image should be less, right? So how is this image compression achieved? How is the compression achieved means we are doing the data compression, right? So if what are we doing is we are trying to compress the data that is required to represent the image. That data we are trying to compress, so then we call that image has been compressed, right? So what actually is data compression? Data compression means reducing the amount of data required to represent a given information. So here the important point that we have to notice here is data as well as information are two different terms. They don't represent the same term, right? So what actually is data and information means? Data means it is by means by which information is conveyed. So for example, if we consider right, if we consider a small, we'll consider a small example where we have uh, say some example like image. Okay, we have the word which is the image. So there are different ways by which this word image can be represented. First is by English letters, right? Second is by using bits, right? The other can be symbolic, right? These can be the different types of ways by which the word image can be represented. So here image is called as the information. And how this information is represented is can be of any of these three types. So this is called as the data. So data means by which the information is conveyed. So to understand it much better, let's consider an example here, a statement, right? So we will consider an example here, which is a statement 1, right? Your friend Harsha will meet you at Rajiv Gandhi Airport in Hyderabad at 5 minutes past 6 p.m. tomorrow night, right? What is the second statement is your friend will meet you at Rajiv Gandhi Airport at 5 minutes past 6 p.m. tomorrow night. If you consider the third statement, Harsha will meet you at Rajiv Gandhi at 6 p.m. tomorrow night. So what is the information that is being conveyed here? Harsha is a person who is going to meet at Rajiv Gandhi Airport, right? He's going to meet you at Rajiv Gandhi Airport at 6 p.m. tomorrow night, right? So this is the information, and these three statements are three different ways by which this information can be representation. So this is, we can say as data set 1. This can be call it as data set 2. This we call it as data set 3. So there are three different ways by which the same information is conveyed, right? So this is the data. Now if you observe more clearly, we observe that same information can be conveyed in different types of data, and we observe that same information is conveyed but different levels of redundancy, right? What do you mean by redundancy? We'll see in later next slide. But if you observe here, there is a first statement is having containing maximum redundant data. So same information is being conveyed by different data means, say which data is best means we will decide based on redundancy, right? So what is redundancy means? Redundancy data or redundant data is the data representation that contains repeated or irrelevant information, right? So let's go back to our previous example. So if we go here, we observe that, so let's check this three statements. If we observe that the actual information is Harsha meeting tomorrow night at Rajiv Gandhi Airport, right? So the irrelevant information is your friend will meet you, right? With the airport is at Hyderabad, so this all can be called as the irrelevant data. So if we remove it a little, so let's see the second statement here. Your friend will meet you at Rajiv Gandhi Airport at 5 past 6 p.m. tomorrow night. So this is the, if Hyderabad, the Hyderabad word, the name of the person. So these, if they are called as the irrelevant data, then the 5 past here, 5 past 6 p.m. tomorrow night can be called as the redundant information. So let's come to the third statement, which is very concise. We can see that Harsh will meet you at Rajiv Gandhi airport at 6 p.m. tomorrow night. So this is a very concise way of telling that a person is meeting you, will meet you at Rajiv Gandhi airport, that too tomorrow night. So the same information can be conveyed, and the first statement is having lot of redundant information. So the redundant data means data representation that contains repeated or the irrelevant information. Now let's consider that B and B dash are different data representations of the same information. Like how we have considered in a previous example, statement 1, statement 2 and statement 3. They are the three different statements by which the same information is conveyed. So here we are considering that B and B dash are different data representations of the same information. Then we call the compression ratio as capital C is equal to B by B dash, right? We call the compression ratio as C is equal to B by B dash. Now, what is the redundancy that is existing in that data representation is given by capital R is equal to 1 minus of 1 by C. So these two are very important in our present topics, that is the image compression techniques, where the image compression as well as redundancy are important parameters by which compression technique should be chosen, right? So here, if compression ratio is given by C is equal to B by B dash, and your redundancy is given by R is equal to 1 minus 1 by C, right? So what are the different types of redundancy that are existing in our 2D intensity array? So what is this 2D intensity array? It is actually the image, right? So we will see what are the types of redundancy that are existing in our image. So first one is the coding redundancy. What is coding redundancy? Each of the intensity value will be coded value of the intensity. Coded value of the intensity. So these, because of this coded value of the intensity, we get the coding redundancy. Next is the spatial as well as temporal redundancy. So this is existing because of pixel positions. Okay, this is the information or the redundancy because of the pixel position. Third one is the irrelevant information, right? So the three types of redundancy that are existing in our images are coding redundancy, spatial redundancy, and irrelevant information. So irrelevant information can be that in an image, say suppose this is a image, okay, right, this is the object on which we have focused. Say suppose this is a hat on which we have focused, right? So the background here, if it is having some other objects and all, so that we can call it as irrelevant information. So if we can just remove, because that is not our focus, then we can, if we can remove this, then we can remove our irrelevant information, right? So what is coding redundancy and spatial redundancy, we will see now. What is types of redundancy? The first one that we are talking about is the coding redundancy. So what is coding redundancy means? Before we go further, let me talk about few words that few keywords that we are going to follow from now onwards, right? So first one is the code word. It is the information or the event is assigned a sequence of code symbols. So what does that mean? Means, say suppose I have intensities, I have an image I. And I have a group of intensities in that, which are represented by R0, R1, R2, R3, R4, so on, and Rn. So I have, say suppose I have image I, and the number of possible intensity values are R0 to Rn. The actually generated image is having, say suppose I am having the matrix as R0, R0, Rn, R3, R7, R5, R2, R11, R32, R52. Say suppose I have an image which is generated, I have an image of 3 cross 3 which is having the intensity values as shown here. This is the possible number of intensity, this is the possible intensity values. Okay, this is the possible intensity value, and this is the image. Let me call it as IP instead of I so that we don't get confused. So this is the image IP. So this is the image IP, right? So this IP is the image which is of size 3 cross 3 generated, and it is having R0, Rn, R3, R7, R5, R2, R11, R32, R52. Okay. Now, so each symbol or each intensity value here, say suppose R0, Rn, R3, they are called as the code symbols. So R0, Rn, R3 are the code symbols. Now, the sequence by which R0, Rn, R3 are the sequence in which this intensity values are placed in our image is given by the sequence R0, Rn, R3, right? First row is given by this. So this sequence of our code symbols is said as code word, right? Yes, so now we understood what is a code word, what is the code symbol, right? Now, if I consider the number of bits to represent the intensity values is equal to B, then the length of the code word can be given by the number of bits. So here, if B is the number of bits to represent the intensity values of an image in m cross n, then the length of the code word is given by, or it can be represented by L of R, which is given by the number of bits, which is B, right? Now, assume that the number of bits used is same for all pixels. That means R0 is represented by, say suppose for example, we will consider for an example, if R0 is represented by 4 bits, then we are assuming that all bits are represented by 4 bits. Then such type of representation is called as fixed data. If all the intensity values are represented by the same number of bits, then we call it as, the number of intensity values are represented by same number of pixels, then we call it as fixed we call it as fixed length, fixed length code, fixed length code. Okay, here if it is the same for all pixels, then the length of the code word L of R is given by the number of bits that is represented. So if it is B, then the total number of pixels that are required, total number of bits that are required to represent the image. So image is of size m cross n, image is of size m cross n. Then if each intensity value, for representing each intensity value, each pixel, for representing each pixel, we require b number of bits, then m cross n image will have m cross n number of pixels. So representing this, we will require m cross n cross b, right? Since we are using fixed length code system, your b can be represented by L of R, so your code word, right? So we can represent the number of bits that are required to represent a fixed length coded image is given by m cross n cross L of R, right? Now, if the code word is dependent on the probability of occurrence in the image. So what does that mean is, in a previous example, we have seen that all pixel values are represented by same code length. So they are all represented by the code length. So it is called as the fixed length code, right? So we call it as fixed length code. Now, if say suppose I have a 5 cross 5 image, 5 cross 5 image, in that only at one pixel I have the intensity value 255, right? So I have only one pixel value which is having 255, and I have to represent this intensity value. So how many bits are required? 2 power 6, right? So to just represent one pixel value, I require 6 bits to represent the same intensity value, but it is occurring only once. So there is wastage of number of bits that are used. So instead of that, if based on the probability of the occurrence of the intensity value, if we can code, then we can reduce the number of bits that are required. By in turn, we can reduce the bandwidth that is required to transmit the image. At the same time, we can always also reduce the power that is required to generate this image. So for these purposes, we will always go for variable length coding, where the code word is dependent on the probability of occurrence of it in the image. Okay, right? So the code length, instead of representing this 255 by 6 bits, if since it is having least possible probability, if we can represent it by 1 bit, then we can reduce almost 5 bits, right? So it is easy for us to compress the image. So for image compressions, for reducing this coding redundancy, we will go for variable length code, right? So variable length code is our best possible way by which an image is reduced. Image can be compressed. Now when we are using the variable length code, the L average, or the number of bits on an average that is required. L average means the average number of bits that is required to represent the image of size m cross n is given by L of R into probability. So this is another important equation that we have to remember. L average is equal to sigma of k equal to 0 to capital N minus 1 L of R into probability, right? So here if we observe, the number of bits that are required is dependent upon the number of bits that are required to represent the code is dependent upon the probability, which in turn will change our L average, So how does it affect? Means if the total number of pixels that are required to represent our image now will be L average into m cross n, right? So previously, when we used fixed code word, when we used fixed code word, code length, to be more specific, then your L average was equal to L of R, right? So your total number of pixels, the total number of bits that are required to represent your whole image was M cross N cross L of R, right? Now it is M cross N into L average, which is dependent upon your probability as well as your code length. So to understand it better, let's go for a small example, right? Here, if you observe here, there are few intensity values, which is 87, 128, 186 and 255. So the possible number of intensity values are 87, 128, 186, 256. So the probability of this each intensity value is given in this column, right? So the probability of occurrence of the 87 intensity value is 0.25. The probability of occurrence of the intensity value 128 is given by 0.47, so on and so forth. Now, in code 1, we are using the concept of fixed length. So the code 1 here is, code 1 is fixed length code. Okay, if you observe here more clearly, your R is equal to 255 value, it is having the least probability, but still we are using the 8 bits to represent our intensity value, whereas the highest probability value is also represented, the highest probability intensity value, which is 128, is also represented by 8 bits. So here it is a waste of number of bits, right? So for to compress this, we are going for variable length coding. So how does it happen? We will see in this later on this slide, in this example. Okay. Now for the first, let me first calculate the L average and the total number of bits that are required to represent the image when code 1 is used, right? So what is L average here? If we are using fixed code length, L average is equal to the length of the code, length of the each code. So L average here is 8. Okay. Now L average is 8. Now what is the, to represent 1 pixel or the 1 pixel, that means 1 intensity value, we require 8 bits. We require 8 bits. So we have here M cross N, that is equal to 1, 2, 3, 4, right? So we have 4 intensity values. We have 4 intensity values. So that can be represented by 4 into 8, that is equal to 32 bits, right? So your L average is equal to 8 bits. So L average is equal to 8 bits, and your total number of bits that are required to represent total pixel values is 8 into 4, which is equal to 32 bits. Now, see, suppose we have used some compression technique and we have generated a code 2, which is here, where the code length is dependent upon your probability of occurrence. Okay, if you observe here, we have represented the code length, which is dependent upon our probability of occurrence. So if you observe more clearly, with highest probability, if the intensity value is having the highest probability, we have given the least number of bits to represent, whereas if it is the lowest, then we have given the highest number of bits to represent it. So if code 2 is given as shown here, what will be the L average and total number of pixels that are required? So let's see here. Let's calculate here. So let's calculate L average, the number of pixels that are required for when code 2 is given. So code 2 is a variable. It is a variable length code. It is a variable length code where the code length is dependent upon the probability of occurrence. So the L average is given by, how we calculate the L average? It is given by this formula, where K is equal to 0 to 3 LR into PR of R. So L average is equal to length of the first code, which is given by the probability length of probability of R of 87, which is equal to 0.25, and the length of the code that is used for to represent the intensity value 87. So we can write it as 2 into 87, right? So next, what is the next is the intensity value is the 128. So what is the code length that we have used to represent is 1, and the probability of occurrence is 1 into, so we can write it as 1 into 0.7. Similarly, we have the next intensity value is 187, where the probability is given by 0.25 into the length of the code is 3, right? Plus, what is the next intensity value? 255. It is having the code length 3, and it is having the probability of occurrence is 0.03. So we can write it in this form. So we get the L average value as, we get the intensity value or the L average value as 2 into 0.25 plus 1 into 0.47 plus 3 into 0.25 plus 3 into 0.03. So that will be our L average value. Now, what will be the number of pixels that are required to represent this is equal to, if L average here the value is 0.75 plus 0.45 plus 0.75 plus 0.03. So we get the values as, say suppose 0.75 plus 0.75, it is equal to some 2. We get approximately around 2. So it means that 1 pixel, if we get L average is equal to 2, if L average is equal to 2, it means that to represent our total pixels, to represent our total number of pixels, we require L m cross n into L average, right? So m cross n is 8 into 2, right? So we require only 16 number of bits, right? So before, when we used fixed length coding, we required 8 cross 4, which was 32. Now we require, now we require 2 cross 4, which is equal to 8 number of bits. Okay. Now let me calculate the compression as well as the redundancy when code 2 was used. So this value is approximately 2. So we got this as here. So the total number of pixels values required is equal to 8. So what is the compression ratio? How do we calculate the compression ratio? As C is equal to B by B dash. So what is the B means? The number of bits are required, that is represented using the fixed length. So that is given by 8. B dash is given by the number of L average, that is given by the to represent when code 2 was used. So that we got around as 2. So this we get the compression ratio as 4. So which implies the redundancy is given by 1 by 1 minus C. So that is 1 by 1 minus 4, which is equal to 75%. So we can write it as 75%. So this implies that when code 2 is used instead of code 1, so when code 2 is used, 75% of our coding redundancy has been reduced. So for this reason, we go for variable length coding redundancy, right? Variable length coding techniques, right? So the next type of this redundancy that we are going to talk about is the spatial redundancy. So the spatial redundancy is related to the interpixel correlations within an image. So spatial redundancy is the interpixel correlation within an image. So what happens is, visual contribution of a single pixel is redundant. How is that redundant? It can be guessed from the values of its neighbors. So since we consider, to understand it better, let me consider an example. Okay, let me consider an example of 5 cross 5 image. Okay, let me consider a 5 cross 5 image. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So Let me, for simplicity, I consider 4 cross 5 image. For simplicity, let me consider this 4 cross 5. So what happens is, I will consider my 8 neighbors. I will consider my 8 neighbors. Okay. So if I consider the pixel 7, so what is my 8 neighbors? I consider 1, 2, 3, 6, 8, 11, 12, 13. Right? Now, if I consider the pixel 8, pixel 9, so what is its 8 neighbors is 3, 4, 5, 8, 10, 13, 14, 15. Right? Here, if we observe that this row, which is given by this row, which is given by 3, 8, 13. This information is replicated as 8 neighbors for 7. It is also replicated as 8 neighbors for my 9. So this type of information is called as our spatial redundancy. So single pixel is redundant and it is guessed from the values of the neighbors. So instead of using this row, if we can compensate this row and the values are dependent upon our neighbors, then we can reduce our spatial redundancy. So this type of redundancy can also exist in this type of the redundancy can also exist in single frame or among multiple planes. Say suppose this is our single plane image, it can happen in single plane as well as we have multiple planes like in our video. In our video we have multiple planes of our image, so the redundancy, if this pixel kind might be a neighbor for this pixel as well as another pixel here, so the same information is being conveyed at multiple frames also, so we call it as spatial redundancy. Right, it can be solved using predictive coding, bit plane coding, and run length coding. So all these coding techniques we will see, and how the spatial redundancy is reduced we will see further. Right, so before we go further we need to have further information about the measuring information. Right, what is the image information that is existing? Right, so for that let me consider this point, like if an event E is occurring, if an event E is occurring with the probability P of E, then the amount of information that exists in the event E is given by I of E is equal to log of 1 by probability of E. Right? If the event E is occurring with the probability of P of E, then the amount of information that is existing in that event is given by I of E, which is equal to log of 1 by probability of E. Right? The units that are used to represent this, units for this is given by usually we use bits. Okay, otherwise it is decided by the base of the log function to decide the units to measure information. Most common unit is the bits. Okay, now if a given a source has discrete set of possible events as A1, A2, A3, A and so on, then the probability of occurrence is P of A1, P of A2, P of A3, so on till P of A1. Then the average information per source output. The average information per source output is called as the entropy. Okay, it is called as the entropy, that is given by minus of summation I equal to 0 to n p of probability of the event into log of that probability. The units is given by bits per pixel. If information is given by bits, then the entropy is given by bits per pixel. So these two information I of E and as well as the entropy are two important parameters by which we even decide the image compression technique. Right? Now, what is the image compression model? How can we decide the how can we draw a block diagram for it? So that we will see now. We have basically decide the block diagram for image compression model as first we have an input image, where it is given to an encoder, we get a compressed image, we get compressed image, we get a compressed image. So from this compressed image, if we give it to a decoder, to obtain our decompressed image. We get a decompressed image, right? So we have an encoder as well as a decoder. So what are the sub blocks which are exist in the encoder are: first one is the mapper, second one is the quantizer, third one is the symbol coder. So we have to revert back all these operations when in our decoder. So that is done by, we have a simple symbol coder, so we have a symbol decoder, we have a mapper, so that is, we have an inverse operation for it, that is given by inverse mapper. There is a no inversion operation for quantization, right? So if you observe here, in an encoder we have the quantizer block, but whereas in our decoder we don't have the quantizer or dequantizer block. So it means that it's actually the quantization operation or the quantizer operation, whatever it is performed, it cannot be reverted back. So this is a very important block that we have to be very careful about, right? So what does the symbol mapper and quantization do is we will see now. So what does this mapper do is it transforms the input image f of y to f dash with reduced spatial and temporal redundancy. So it, the first block, which is the mapper, will try to reduce the spatial redundancy. So that can be achieved using the RLC coding, right? The next block is the quantization. We have to choose the best quantization method to achieve, to reduce irrelevant information. So using the quantization, we are able to reduce the irrelevant information. So after that, we have the symbol coder, which will generate the fixed or the variable length code to represent the quantized output. So this symbol coder will reduce the coding, this will reduce the coding redundancy. So if we observe that all the three blocks that are existing in our encoder will try to reduce each of the redundancy that is available in our image, right? So the mapper tries to reduce the spatial redundancy, the quantizer tries to reduce the irrelevant information, whereas the symbol coder tries to reduce your coding redundancy, right? So we have in our coding, a symbol coder will generate either fixed or variable length code. In our previous example, we have seen that the variable length code is best possible. We can have lot of redundancy that is can be achieved. So we will continue our image compression techniques as variable length coding, right? So what are the different types, or the types of the variable length coding techniques that can exist is lossy techniques, lossy techniques, and the lossless, or we can call it as error free. Since it is lossless, we can call it as error free compression techniques. So we will see further what are these lossy techniques and the lossless techniques that are existing. We will also see the predictive coding techniques in our further videos, right? So here if we observe that the quantization, we have to choose the best quantization method. So what are the quantization methods that we will use mostly here is the delta modulation. So let me write it here: delta modulation, first one. Second one is differential pulse coding technique. Okay, so these two are best quantization techniques that are used for reducing our irrelevant information. To reduce the coding redundancy, we are going for variable length coding. We have two techniques, which is the lossy techniques and the lossless techniques. And to reduce our spatial redundancy, we are going for RLC coding, right? So we will see in our further due course how each lossless technique is defined, and how are they help in reducing the variable length or the coding redundancy, right? This is the Gonzalez books, from where the coding techniques as well as the information image fundamentals can be used, right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.